Good morning to all of you. My name is Sahkun and I am working as an assistant professor in Information Technology branch at IIMT College of Engineering. Today I am going to illustrate the topic Pushdown Automata, that is a crucial and important topic in theory of automata and computer and formal languages. First of all, I will illustrate what is Pushdown Automata. Just as a DFA is a way to implement a regular expression, a push-down automata is a way to implement a context-free grammar. PDA equivalent empowered to a CFG can choose the representation most useful to our particular problem. Essentially identical to a regular automata except for addition of a stack. The stack is of infinite size. The stack allows us to recognize some of the non-regular languages. As you all know that finite automata can read regular languages and there are some constraints in finite automata. In finite automata, there is a lack of memory. Due to lack of memory, finite automata cannot read context-free grammar as well as context-free languages. To overcome such type of limitation, the term PDA comes in shuffle. In PDA just like finite automata, but having some storing capacity also. We can say PDA is an extended version of finite automata with a stack, as you can see here. Finite state control, accept or reject a string, and this is the basic structure of any finite automata machine. Now, in PDA, a memory in the form of a stack is added with finite automata. With the help of this stack, we can read all types of languages. It may be in form of regular expression, it may be in the form of regular grammar, or it may be form of context-free grammar. With the help of the stack, we can store it in auxiliary memory. Implementing a PDA in one transition, the PDA may do the following: consume the input symbol. If null is the input symbol, then no input is consumed. Go to a new state, which may be the same as the previous state. Replace the symbol at the top of the stack by any string. If this string is null or epsilon, then this is a pop of the stack. The string might be same as current stack top, does nothing. Replace with a new string, pop and push. Replace with multiple symbols, multiple pushes. Informal PDA examples. Consider the language L equal 0 to power n, 1 to power n, where n is greater than equal 0. This is a language. We showed this is not a regular. This language is not a regular. We have already proved it with the help of pumping lemma that 0 to power n or 1 to power n, where n is greater than equal 0, is not regular. Now, a finite automata is unable to recognize this language because it cannot store an arbitrarily large number of values in its finite memory. Now, this problem can be solved with the help of PDA. A PDA is able to recognize this language, can use its stack to store the number of zeros it has seen. At each zero is read, push it onto the stack. As soon as one are read, pop are zeros of the stack. If reading the input is finished exactly when the stack is empty, accept the input, else reject that. The simple logic behind Implementation of PDA for this language is that whenever we get 0 as an input, we will push it into the stack one by one. First 0 comes, then we will push it into the stack. Second 0 will come, then we again push it into the stack. Third 0 and so on. Now, suppose we push n number of zeros in the stack. Now it is a turn of 1. When our PDA or our machine get 1 as a scan symbol, then one pop operation will be performed, and one pop means at the top of the stack is the 0. First 0 will be removed out. After second one is scanned, then second pop will be executed and second 0 will be popped out and so on. Suppose we pushed 5 number of zeros, then we have to perform 5 pops. At the last pop, only one stack symbol Z0 will be remained in the stack. And there are two things. We can pop it also Z0 and our stack will remain empty. This is one criteria to accept any language, that if our stack is empty, then that language accepted. If our stack is not empty and we reach to the final state, it is a second criteria to accept that language. PDA and determinism. The description of the previous PDA was deterministic. However, in general, the PDA is non-deterministic. This feature is crucial because unlike finite automata, non-deterministic adds power to the capability that a PDA would have if they were not allowed to be deterministic. That is, a non-deterministic PDA can represent languages that a deterministic PDA cannot. As we all know that finite automata is categorized in two ways: deterministic finite automata, non-deterministic finite automata. Non-deterministic finite automata is an extended version of deterministic finite automata. It has more powerful capability in comparison to deterministic finite automata. Same as finite automata, PDA can also be categorized into two ways: non-deterministic PDA and deterministic PDA. Non-deterministic PDA has more capability in comparison to deterministic PDA. We will discuss in next slides also. Formal definition of a PDA. There are 7 tuples in a PDA. Any PDA has 7 tuples. What are those tuples? First is capital Q, second is sigma, third is gamma, fourth is delta, fifth is Q naught, sixth is Z naught, F is the final step. Q, what capital Q signify? Capital Q signify finite set of states like the finite automata, as we already know, that is any machine, any finite machine, any finite automata machine. It may be a PD or it may be a finite automata, have certain set of states. That all states is signified with the help of capital. Capital Q is a set of states. Capital sigma, finite set of input symbols. As we all know, what is input symbol? Any string is made with the help of input symbols. Input symbols may be 0, 1. Input symbol may be small a, small b, and small b. So whatever input symbols in a string, that will comes in sigma. Gamma, finite stack alphabet. As we already know that PDA has a stack facility that is used to store symbols. So whatever symbols that we can comes in a stack, all symbols is represented with the help of gamma. Q0 is the start state, Z0 is the start symbol, So whatever start symbol is in stack, it is represented with the help of Z or Z0. Initially, the PDA stack consists of one instance of this start symbol and nothing else. We can use it to indicate the bottom of the stack. Capital F set of final accepting states. So there are 7 tuples: Q, sigma, gamma, Q0, Z0, capital F. In any PDA, we can define these 7 tuples. Now, PDA transition function, that is delta. Delta transition function, which takes the triple delta Q comma A comma X, where Q is the any state in capital Q, the small a input symbol in sigma, capital X is stack symbol in the gamma. The output of delta is the finite set of pairs P comma gamma, gamma, where P is the new state and gamma is a new string of stack symbols that replaces X at the top of the symbol. So there are 3 conditions. If gamma equal to null, then we pop the stack. If gamma equal to X, the stack is unchanged. We are neither pushing any symbol into the stack or we are not. We are popping out. If gamma equal to yz, it means then X is replaced by Z and Y is pushed from the stack. No, the new stack top is to the left hand. Formal PDA example. Here is a formal description of PDA that recognizes language 0 to power 1 and 1 to power n, where small n greater than equal 0. Here, what are the different states? Q1, Q2, Q3, Q4, sigma 0, 1, gamma 0, Z0, capital F equal to Q1, So this is the tabular representation of a PDA. Suppose input is at initial state is Q1 and we are getting null, then we are moving to Q2, Z. And this is a tabular representation of PDA. This is the graphical representation of a PDA. Q1 and the starting state is Q1 and final state is the Q4. At the Q1, we are getting null and stack at the top of the stack is Z0. Then it will remain Z0. We are not doing pushing and not popping out. And just we are moving to the Q2 state. And the Q2 state, if we are getting input 0 and at the top of the stack Z0, then we are pushing it into the stack and so. So this is a graphical representation of a PDA. Now third is instantaneous description of PDA, that is in short form it is called ID. For a finite automata, the only thing of interest about FA is its state. For a PDA, we want to know its state and entire content of its stack. Often the stack is one of the most useful pieces of information since it is not bounded in the size. We can represent the instantaneous description ID of a PDA by the following 3 tuples. Triples. Q is the state, W is the remaining input, and gamma is the stack content. By contention, the top of the stack is shown at the left end of the gamma and the bottom at the right end. Language of a PDA. The PDA consumes input and accepts input. When it ends in the final state, we describe this as. So this is the way a language is accepted by PDA or not. That is, from the starting state, we can make moves that end up in a final state with any stack value. The stack values are irrelevant as long as we end up in the final state. Such type of languages a PDA generates. Now, how PDA accept? A language can be accepted by push-down automata using two approaches. First one, acceptance by final state. The PDA is set to accept its input by the final state if it enter any final state in 0 or more moves after reading the entire input. If we are reaching, our PDA is reaching to final state, then we can say that this string is accepted. Or second one is acceptance by empty stack. On reading the input string from the initial configuration for some PDA, the stack of PDA gets empty. This is the second criteria to accept a language by PDA. If at the last our stack is empty, then we can say that this string is accepted by PDA. Now, we can categorize PDA in two forms: deterministic PDA, that is this short form DPDA. A DPDA is simply a push-down automata without non-determinism. That is no epsilon transition or transition to multiple states on same input, only one state at a time. DPDA not as powerful as non-deterministic PDA. This machine accepts a class of languages somewhere between regular languages and context-free languages. For this reason, the DPDA is often skipped as a topic. In practice, the DPDA can be useful since determinism is much easier to implement. Parsers in programs such as YACC are actually implemented using a DPDA. Non-deterministic DPDA, with the help of these two graphs, we can difference, we can create difference, or we can understand difference between DPDA and NDPDA. As we can see here, Q1 state and we are getting A input, then we are moving to a new state. That is a DPDA. In NDPD and NDPDA, if we are at Q1 state and we are getting A as an input symbol, then we are moving to different states. That is a non-deterministic DPDA. So how we can create differences between NDPDA and DPDA? There are some differences. DPDA, deterministic push-down automata, NDPDA, non-deterministic push-down automata. First point, it is a less powerful than NDPDA. It is more powerful than DPDA. It is possible to convert every DPDA to a corresponding NDPDA. It is not possible to convert every NDPDA to a corresponding DPDA. The language accepted by DPDA is a subset of language accepted by NDPDA. The language accepted by NDPDA is not a subset of language accepted by DPDA. The language accepted by DPDA is called DCFL, deterministic context-free language, which is a subset of NCFL, non-deterministic context-free language accepted by NDPDA. The language accepted by NDPDA is called NCFL, non-deterministic context-free language. Thanking you. This is a small description of push-down automata. There are more in push-down automata. If you have any query, you can ask me to comment section. I will try to resolve your queries. Thank you very much.